Hey everyone, I'm Kobe, and in this video I'll be talking about the longest common substring problem and how to solve it in linear time. So the problem goes as follows. You have two strings, x and y, of total length n, over some constant sized alphabet, and the task is to find the longest common substring between those two strings. So this is a really famous problem in computer science. It's a really famous interview problem, and it's seen a lot in algorithms courses, but also in fields like biology. You could use this to kind of find similarities between, I don't know, two viruses by just analyzing their DNA sequences. But anyway, here we have a toy example that kind of shows how it's done. X and Y, we find that the longest common subsequence, just by looking at them, happens to be CT. Now, that's fine for such nice small examples, but in the real world, where we have DNA sequences of maybe billions of characters long, we want something that can run fast at scale. So in class, we did talk about a method using dynamic programming, and that built a 2D DP table that maintained the longest common substring up to an index of both strings. And so that allowed us to kind of just build up to a final solution as we went along. The problem was that ran in O of n squared time and used O of n squared space, which in fairness could be optimized down to O of n with some tricks. But in the real world, we'd ideally want something that is proportional to the length of the string. In other words, something that could run in O of n time. And we also don't want to sacrifice any space complexity by doing this, so we also want something that only takes O of n space. And that's exactly what I'm going to be talking about in this video, is how to achieve this using a neat little data structure called suffix trees. Alright, so now I'm going to be talking a little bit about what suffix trees actually are. So a suffix tree is nothing else but a tree that has some of the following properties. First is that it has n leaf nodes, where n is going to be the length of your input string. Also, it has these internal nodes, so all the non-root and non-leaf nodes. All of those internal nodes will have at least two children. And you'll notice all the edges are marked with a substring in S. And in fact, no two edges coming out of the same node will start with the same character. So for example, at the root node, you'll notice one starts with a $sign, one with a B, an X, and an A. They're all unique. You can't have any with the same starting character. And if you were to walk from the root to any of the leaf nodes and pick up all the substrings you encountered on the edges along the way, you would end up with a suffix in S. So for example, if I started at the root, I took this edge, I pick up that A, I end up here, and I take this edge, pick up the BXA $sign, and end up in this node, I'd have the string ABXA $sign, which is a suffix in S. And all this number inside the leaf node tells me is where in the original string that suffix started from. So for example, this one says I started from index 1, and we can see that's true. That is ABXA $sign. Now, this $sign at the end wasn't there before in the toy example, and what that is just what's called a terminating character. So the terminating character is what we as the implementer have designated to be a character that is 1, not in the alphabet, and 2 will appear nowhere else in the string except at the end. And to see why it's useful, take a look at this example on the right. So this is the suffix tree for the string XABXA. There's no terminating character here. And you'll notice right off the bat that this tree looks a lot different from the one we had before. And so here I have the suffixes of that string, and the first 3 strings, inserting them really isn't a problem. In fact, the tree as it is right now is what it would look like after the first 3 are inserted, and is actually the final tree. And the reason that we have a problem is because of this XA and A. So these are 2 suffixes that happen to be prefixes of another suffix. The XA is a prefix of this suffix, and the A is a prefix of this suffix. And the reason it's a problem is because that we don't actually have any branches for those suffixes. And to see why, let's try inserting the XA. So if we tried inserting XA, we take this edge, since the X matches, we continue along it because the A also matches, but then we run out of characters to process, so we have no reason to branch, we just kind of stop there. Also for the A, we take this edge, and then stop after the A, because we have nothing else to process, and we haven't branched. So you'll notice that we only have 3 leaf nodes for a tree that should have 5 suffixes. And the reason for that is because we didn't have a non-repeating character at the end of our string. If you look at this tree on the left, this $sign kind of forces us to create a branch or an edge split that adds that extra node for that new suffix. We didn't have that here, so these suffixes are actually implicit. And for that reason, this is called an implicit suffix tree. We don't have an explicit suffix for every single possible. We don't have an explicit leaf, sorry, for every single possible suffix in our string. And so for that reason, we tend to just stick to the suffix tree of the form on the left whenever we do any kind of string-related problems that rely on suffix trees. And that's what I'll be focusing on for the rest of my presentation as well. So now that we know a little bit about suffix trees, let's talk about how we can use them to solve our initial problem. So here is the generalized suffix tree for the string xy. All a generalized suffix tree is a suffix tree that represents more than one string. So in the previous slide, we had one for just a single string, whereas now we have one that represents both x and y. And the simplest way, in my opinion, to make a generalized suffix tree is to just concatenate all the strings you have initially into one string, where each of them have their own unique terminating character, and just build a suffix tree using that. And as you're building it, you actually keep track of which original string that substring belonged to. And so that's what we have here. If you look at all the leaf nodes, they're all colored. And that just tells us which string this substring belonged to. So for example, this pound sign is green, so we know it belonged to X, whereas this $sign is blue, so we know it belonged to Y. Anyway, in order to go about finding the LCSS, what we first have to do is find pretty much all the common substrings between them. And the way we do that is by identifying all the internal nodes, so all the non-leaf nodes, that have both a blue and a green leaf somewhere in their subtrees. So if I just were to color all of those nodes in, that'd be this, 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 and this. So it turns out in our case that all of the internal nodes meet that criteria, but that's not always going to be the case. So anyway, what all these nodes represent is all of the possible substrings that X and Y have in common. Here we have the A, they both have that in common. We have the C and the T, they both have those in common. And that's the same deal over here. Anyway, to find the longest common substring, because these are just the common substrings, to find the longest one, we need to find the deepest such node, which just by eyeballing it is this one right here. But if you were to implement this programmatically, you just run a DFS to find that. And what actually gives us the longest common substring is just the substrings we pick up along the way from the root to this node. So if we start at the root, we pick up the C, we pick up the T, and then we get there and we stop. And as we know from earlier, our answer was, in fact, CT. And this makes a lot of sense, right? Because what we're saying is that at this point, X and Y had something in common. And at this point, X and Y had something in common. And then here, at the lowest possible node where they could diverge, they diverge. So afterwards, they're different. But up until then, they were the same at some points. And so that gives us the CT. And you'll notice that we've actually done this in linear time. Because to find these nodes, to find the lowest one at least, you had to run a DFS. And the DFS will touch all of the n leaf nodes, which means we incur order and runtime. And we actually will only have n leaf nodes, so that means our space complexity is also going to be order n. So as you can see, suffix trees are great for this problem because we can do this in linear time without much effort. Now, the problem with suffix trees is actually building them in linear time. So the trivial algorithm runs anywhere between order n squared to order n cubed time, depending on how cleverly you implement it, that is. And so the problem is that we already know that our dynamic programming solution also gives us order n squared time, and it uses either linear or quadratic space. So we want something better than this ideally. And thankfully, we can actually reach order n time while still maintaining that nice order n space complexity by using a clever algorithm invented in, I believe, 1995 by Ukkonen. And that algorithm basically takes the trivial implementation and introduces a series of clever tricks and optimizations that will take, when combined, will take that n squared runtime and bring it down to order n. And that's what we're going to be talking about next. So now that I've kind of hinted at what Ukkonen's algorithm does and how it relates to the trivial implementation, I think it makes the most sense to first talk about how the trivial algorithm goes about constructing a suffix tree. So I have the same string here as we had on the previous slide, XAB, XA $. I've also listed out suffixes, and we're going to go through how to create a suffix tree with this now. So typically, for the sake of illustration, I'll be going from the largest suffix to the smallest one when I insert, but in reality it doesn't really matter which order you do it in because the suffix tree will look the same at the end. But anyway, so first step, we just start by adding our root node, and once we have that, we can start our iteration. This would be a for loop programmatically, but here I'm going from the largest to the smallest suffix. So in our for loop, for example, we'd start at iteration 0, and we'd work our way to the right. So if we're on iteration 0, that means we're processing this suffix currently, and we notice that currently from the root node there is no edge that that begins with x, so we just create one, and we insert the suffix there. So a x a b x a $. And since we're on iteration 0, we know that this suffix started at position 0, from index 0. So now we're done with that one. We can increment our, we can go to the next iteration of our for loop. Now we're on this suffix, so index 1. Again, we notice that there is no outgoing edge from the root node that begins with a, so we just make one. That gives us a, b, x, a, $, and that one began from index 1. So now we move on. For iteration 2, we have bxa $, again, same deal. There is no edge that begins with b, so we just create one. bxa $. And that one began at index 2. So now we're on iteration 3, and this, as you might remember from the previous slide, was where we had some problems, right? Because this xa appeared earlier in another suffix up here, and again, we're going to have the same problem later on too. So what happens in this case is programmatically, you could just make this like a variable or something that keeps track of where your active point is or where you're going to be doing the inserting. And that's actually one of the tricks that will kind of help produce runtime. But basically, for the sake of illustration, I'll just be marking it with like a little point. So I'll say this suffix right now is xa, right? And I start from the root node. I notice that one of the edges actually does begin with x, so I take that edge, and that means my active point is now here. I also notice again that the next character in this suffix is a, and that's also in this edge, so I can kind of move my marker up to here. Now from this point, we have a divergence because the current suffix has a $, whereas the edge right now has a b. So that means what we need to do is basically we need to get rid of this edge as it is right now and make a branch. So here I'll make an internal node, and then from that internal node I'll say that there is one path where I just take the $, and that leads me to the suffix beginning at index, what is that, 3? Yeah, 3. And then there's another path, there's another edge where I could just take the original root, which was the first suffix. So that would be b, x, a, $. And that, of course, was the suffix beginning at index 0. So now we've actually correctly handled the case where we had a suffix being a prefix of another suffix. So now we're done with this iteration. We can move on to 4. So now we have a $sign. Again, we're going to notice, so we start back at the root. We notice that we do have an edge that begins with A. So we take that edge, meaning our marker is now there. Again, now we have a divergence because this edge goes AB while this suffix here goes a $sign. So we make another internal node for a branch. So I'll erase this up until this point. Now we make our internal node, and from there we can either take the root where we just go straight to the $sign, and that gives us the suffix starting at index 4, or we take the root where this edge was before, which was just ABXA. BXA, $sign, and that of course was the suffix starting at index 1. And finally, for the last iteration, this one's pretty easy. Again, we look at the root, notice that there's no outgoing edges that started with a $sign, so we just make one. I'll make that the $sign edge, and of course that was the suffix beginning at index 5. So this is our completed suffix tree. It might look a little bit disorganized compared to the one I had in the previous slide, but it's pretty equivalent. This is a suffix tree for the string XAB XA $sign. And so you might notice that you might not notice from just this example, but if you were to implement this the way I've shown it here, you'll notice that it's kind of inefficient because something that's unavoidable is we did have to go through all the characters in the string, which was our outer for loop basically. So that already on its own incurs order n work. But then for each iteration, again, a lot of this depends on how you implement things, but say we were just doing substring searches, so that means all of these edges actually stored literal strings. That would take maybe an additional order n time per iteration to do all those comparisons. And then, of course, you could also do a lot of other implementation changes that could induce another order n work per iteration. So in reality, you're looking anywhere between order n squared to order n cubed work at the bare minimum. And so the goal of Ukkonen's algorithm is to kind of modify a lot of these implementation details and all these algorithmic details to enable us to get to order n runtime. So now that we've kind of went over the trivial algorithm, hopefully this will make a bit more sense. So the first major difference between Ukkonen's method and the trivial one is that he chooses to construct the tree character by character. So basically, scanning left to right, you basically add the characters one by one, and then at the end you'll have the same suffix tree. Now, there's a problem that comes with that too that actually is also present in the trivial one. Say you wanted to actually add another character to this string after you've already constructed the suffix tree. In the trivial implementation, you'd basically have to build the entire tree again because you'd have to add that y to all of the current leaf edges. And that's also a problem in Ukkonen's algorithm if he didn't include a trick for it. So the trick he chose to use to avoid having to visit all n nodes, all n leaf edges, and update all of their values is to change how he represented the substrings. So what he chose to do is basically, instead of storing actual sequences of characters, in other words, instead of storing the substrings as actual strings, he chooses to represent them as just by their start and end indices. So for example, this entire string could be represented as starting from index 0, and ending at index 5, I guess, if you exclude the y. And what he does to avoid having to, manually go through all the leaf edges and add that extra character is use an open end for the string. So rather than give an explicit, index, he chooses to just say, So this string could actually just become 0 to some specific end character, like maybe the pound sign. Now this just represents wherever I'm currently ending the string. So at the end of so if you process the entire string, then this end would just become 5. So to give you an idea of how that works in the tree, let's take this edge, for example. That's just A, so since that's not a leaf, we actually don't even need the end character. We just say that we start at index 1 and end at index 1, and that gives us the character A. Now for this edge, that is a leaf edge, so how we can encode that is that we start at index 2 and go until the end. So that has basically transformed it into a much more compact representation. And now if you notice, if I were to add this y after this tree was constructed, I actually don't have to change much because this end character kind of handles it for me. I'm basically saying implicitly that I've already added this y to the end by just leaving the end character there as it is. All I'd have to update is the end character, so the end character would now become 6. And I'd also just have to add one edge from the root for the y. And that's also, so both of those were also done in order one time. So that's the first neat property, and then next I'm going to be talking about some other information you need as you're constructing the tree. So now that we're doing things character by character, there are a couple more things we need to keep track of as we progress through the algorithm. So the first thing that Ukkonen uses is called the active point. So the active point is nothing but a tuple containing an active node, an active edge, and an active length. So the active node, for the most part, in our examples, has been just the root node, because recall when you initialize in the algorithm, you just start with the root node with no edges or anything like that. So we usually start with the root node. All the active node is just what internal node we're at, and that's going to be the starting point for all of our interactions with the tree. So whenever we want to create a branch, we start from that node. When we want to, eventually create another leaf node or another edge, we start from that node. Now the active edge is just which edge from that node we want to take. So for example, when we were inserting XA, the suffix XA, in the suffix tree from the previous example, we'd first look for an edge that started with X. And so in that case, our active edge would be X. But again, keep in mind, when we initialize, this would actually just be initialized to null, since we have no edges initially. But anyway, and the active length is just how far along down that edge we want to go before stopping to either insert, create a new node, things like that. So the active length is initially 0, but say in the example, after I was trying to insert XA, right? And one of the edges already had XA on them, so in that case, my active length would be 2, because I'd go down the tree, I'd stop after the second A, because that's where I have a divergence. So at that point, my active length was 2. Now, if you couldn't tell, what the active point tells you is just basically where in the tree you're going to be doing the main work of the algorithm. So, for example, with this active point, as I have it labeled right now, I'm saying start at the root node, so start right here, take the edge beginning with X, so this edge, and go 2 characters down. So go right here and then stop. So that's one thing that you need for Ukkonen's algorithm. The other thing you need to keep track of is what's called the remainder. Now, the remainder wasn't really used at all in the trivial algorithm because we were inserting entire suffixes at a time. But what a remainder signifies in Ukkonen's algorithm is how many suffixes we have left to add to the tree. So since we're doing things character by character, you'll notice that at some points when we add a character, this will be more clear later on, by the way, when I walk through this, but at some points when you add a character, that might mean adding more than one suffix at a time. So the remainder just tells us how many suffixes we have left to insert. And this will make a lot more sense when I walk through the example next. So let's walk through a quick example. This is the same string we saw in the previous slides. On the right, I've listed the active point, which is initialized to the active node being the root. The active edge, since there are currently no edges, would just be null. The active length is 0 and remainder is 0. So remember that since Ukkonen's algorithm does things character by character, we'd technically just be having like a for loop or something over the characters in the string from left to right. So without further ado, let's get started with iteration 0. So in iteration 0, we take in this x. Now Ukkonen's algorithm says the first step in general is just to add the new character that you've taken in to all the existing leaf edges. Now currently we don't have any leaf edges, but if we did, we'd add that x to it implicitly, using that representation we mentioned before. So since we don't have any edges right now, I'm just going to go ahead and make one. It starts with x. Now again, I'm going to be listing the substrings here as actual strings, but keep in mind we're still using that compact start and end index representation from before, which allows us to implicitly update all of our leaf edges in order one time. So anyway, I've added this x, which means I've successfully added this suffix as it is right now. So I've added the current suffix from our start index to our current iteration. And because I did that, I can say I've resolved this suffix. And I'll mark that in its leaf node that this is the suffix starting from index 0. Now, technically, I would have incremented the remainder here because before I added the x, I'd said that I have one more suffix to insert, which is just the x, but I've added it now, so that would actually decrement back down to 0. And so for the rest of these simple cases, I won't be actually incrementing the remainder, but just keep in mind that that is happening in the background. So anyway, I'm done with the current iteration. I can now go on to iteration 1, where I take in this a. So again, I add the a to all of the current leaf edges, and then note that there is no branch that starts with a coming from the current active point. So I make one. And since I've resolved that suffix, I've resolved the suffix just a, I can go ahead and mark that as being the suffix starting from index 1, which is my current iteration. Now we go on to the next iteration. I'm on iteration 2. We take in this b, same deal. Add the b to all the leaf edges. Create a new edge for it since there isn't one coming out of the root that starts with b. And I've also resolved that suffix, so I can mark it as being the suffix starting from index 2. So far, so good. Now I go to the next iteration, iteration 3. Now we have some problems because you'll notice that this x that we've taken in is actually repeated. So again, we still do add it to all of the edges implicitly, all the leaf edges. But we notice that there is an edge that starts with x already, and so we don't make a new one because if you remember from the rules of suffix trees, you can't have two nodes, two or more nodes coming from the same internal node that start with the same letter. So instead, what we'll do is we actually won't touch the suffix tree at all. We'll just update our active point. So now our active point becomes this point right after the x on this edge. So if I were to update that in the table, that would be so from the root you take the edge starting with x. So your active edge is x, and the length is 1 because we've gone 1 unit down. So just after the x. And in fact, our remainder is now incremented to 1, and it stays 1 because we haven't actually added the suffix x alone to this tree. You'll notice that we only have 3 leaf nodes, but we have processed 4 characters, which means we should have 4 suffixes, but we only have 3 right now. So this tree is still implicit. So anyway, once we've done that, we don't touch the tree. We go on to the next iteration. Iteration 4. Take in this a. Again, same deal here. We will add that a to all the leaf edges implicitly. And again, we notice that from our active point, the next character again matches the one we've just taken in. So we will not touch the tree at all. We'll just increment or update our active point. So now it's just after the a instead. If I were to update that in the table, the active edge still stays the same because we're saying from the root, take the edge starting with x, and then now we're going 2 down instead of 1. And since I haven't added another leaf node for that new suffix of just a, I will increment the remainder to 2. And still not touch the tree. So now we go to iteration 5. Now I have this $sign. Again, I'll first add the $sign implicitly to all the leaf edges. And I'll also go ahead and I would technically increment the remainder here to 3. But what I'm going to do is just go ahead and first create the edge for it. So there's the $sign. I started at index 5 since there weren't any edges coming from the root node that started with it. But since I've added that leaf, I can now decrement this back down to 2, and then we can continue with the rest of this iteration steps. So now you'll notice that this $sign actually doesn't match the next character on this edge from our active point, which is a B. So that means we need to create a branch. So what I'll do is race up to here, create a new internal node, and from there I have multiple paths. I have the one that we had before, which was just bxa $sign. And that started at, that had the same leaf value as before, which was 0. And I also have this new one for the $sign. And to find out where that started, you can just take the iteration or current end you're at, subtract the remainder, that gives us 3. And you can verify that now we've added the suffix $xa $sign, which starts at index 3, right here. So now we resolve that suffix, which means, again, we decrement our remainder down to 1. And whenever you actually add an internal node from the root, what you do is a quick little trick to save some time is just decrement your active length by 1 and change your active edge to be the next character along your current edge. So now instead of taking the active edge as being x, it'll just become this a. So now what we're saying is the new active point is from the root, you take the edge starting with a and go 1 unit down. So that's this right here. So that helps us save time instead of like rescanning and stuff like that. So what that has done is basically told us that the new suffix we need to insert is no longer xa, but actually just a $sign. Sorry. So again, I'll notice that the $sign doesn't match the next character on that edge, which is b. So I'll create a branch. Create that new internal node. Have the path from before, which was bxa $sign. That kept the same leaf value from before, which was 1. Now I have this new path for just the $sign. And that started from index 5 minus 1, which is 4. And so now you can tell that we've added the suffix a $sign successfully, right here. And with that, we can, again, decrement our remainder, decrement our active length down to 0. And since it's 0, in fact, we can just reset our active point to the root node. Anyway, there's also one thing I didn't mention yet, because it's not really important for this example since it's so short and the representations are also fairly short. But whenever you create multiple internal nodes in the same iteration, it helped later down the line to just connect them with what's called a suffix link. And again, that won't be very apparent in this example, but I'll do another one that showcases that. And what suffix link allow you to do is basically, in order one time, fix suffixes as you go down the line. So for example, this xa, once we fix the xa, we can just instantly jump to the next point, fix the a, and then, if there were more characters in this repetition, keep going down the line. And that, again, that's not really useful here, but we'll see another example that covers that. And so anyway, this is actually our completed suffix tree from what we saw in the previous slides. It's the same thing, but we've done it in order and time. because of course we do have to process all the characters in the string, which takes order and time on its own. That's unavoidable. But during each iteration, we only do order one work. Oops. And that's because of all these tricks we've used. So we've maintained the active point, kept track of how many suffixes we had to insert. We used that fancy little edge label compression method, which converts substrings into just integer tuples. Like this would be, 2 to the end, and yeah, things like that, which kind of narrow down our runtime to order one on average per iteration. So before we actually jump into the next example, I'd like to quickly talk about suffix links a little bit. So the reason they weren't really important in the previous example that we covered, this is the suffix tree for it, by the way, was that in all cases, our active node was pretty much just the root node. And we always actually maintain a pointer to the root node because, thinking about it logically, if we didn't have a pointer to the root node, we would lose access to our tree. So we always have a pointer to the root node, which is why that wasn't a problem. But if our active node is ever not the root node, and we need to end up resolving suffixes like we had before, like for example, the repeated XA was a problem. Whenever we come to cases like that and the active node isn't the root node, we need a quick way to jump to another internal node. So if we didn't have suffix links, what would happen is, say we had our active point around here, this was our active node. Once we resolved this point, once we resolve the suffix here, we'd have to then find the next active point. But the thing is, the next active node would probably be another internal node, not the root. So that means we'd have to, again, start at the root and then kind of scan through the tree to find that new active point and active node, which was going to take, either in the worst case around linear time. And we want to avoid that, which is why we have suffix links. Suffix links, as I hinted at before, just kind of link those nodes together. So the next time you encounter this case where you need to fix a suffix, you can just, instead of scanning from the root, you can just ride the suffix link after you fix that suffix here, and keep riding them until you run out of suffix links to take. So let's get started with a more complex example. So here I have a new string, s equals abc, abx, abcd, and you'll notice right off the bat that not only is it longer, but all of its repetitions are also longer. So anyway, I've already initialized our active point and root and everything. I made the root white because things might get a little bit crowded here, so just so you can keep track of it. Anyway, let's get started with our for loop. So we start with iteration 0. We take in the A. We note that, there are no leaf edges, so we don't add it to anything yet, but there are also no edges coming out of the root that begin with A, so we'll make one. And we've already resolved this suffix, which is just A, so we can increment our remainder, then decrement it again, and we'd make a leaf for it. So this is the suffix starting from index 0. Now moving on to the next iteration. Now we have B. So we add B to all the current leaf edges, and also make a separate branch, separate edge for B, since there is none that exists that start with B. And this suffix is resolved, so we'll say that this is the suffix starting from index 1. Now you go to the next iteration, iteration 2, take in the C, same deal, add it to all the existing leaf edges, and also make a separate edge for it. And that was resolved just fine, so we'll say that this is the suffix starting from index 2. Now next iteration, iteration 3, we have an A. So we will add the A to all of the leaf edges first. And I will note that we already have an edge that starts with A, so we actually don't make a new one. I'm just going to go ahead and increment the remainder right now to 1. And since we didn't make a new edge because one already existed that started with A, we will just move our active point do right here, right after the A. I'll go ahead and update that in the table. So now from the root, our active edge would be the one starting with A, and we go 1 unit down. And then we don't touch the tree after this. So next iteration 4, taking the B, I'll just go ahead and update the remainder 2. So that's 2 now. We will add that B to all of the current leaf edges. And since we already, from our active point, the next character already matches B, so we will update our active point. Now that is right after the B, and I'll go ahead and do that in the table as well by incrementing the active length to 2. All right, we're done with this iteration. Now we go to iteration 5. Taking the X, I'm just going to update the remainder so I don't forget to add the X later, but that's updated to 3. Actually, I'll go ahead and first add the edge starting with X just so I don't forget later. So we make the new edge starting with X. Let me make that a little longer. That's resolved. This is the suffix starting from index 5. So we resolved one suffix. I'll decrement this down to 2. And now we have to handle the other cases. So we have to fix the suffix basically ABX and BX. So let's do that. So from ABX, which we'll first fix that one because that's where our active point is right now, right after this B. So we note that the X does not match the next character on this edge, which is a C. So we need to create a branch. I'll erase this. Make a new internal node. So our old edge was CABX. I forgot to add this X, by the way, implicitly, but that happened. So we have CABX, and that kept its old leaf value of 0. And then we have this new edge for just X, and its value is 5 minus 2, which is 3. So we can verify that from index 3 to index 5, that's what we had, ABX. So now we've handled one suffix, so I can decrement the remainder again, down to 1. And so that also means I can, since our active node is the root, I can just decrement the length down to 1, and also set the active edge to be the next character from my current edge. So right now my active point was like around here. So the old active edge was A, and now I'll set it to be B, which is the next character. And so that tells me that now my new active point is right here after the B. So now again, I notice that the X does not match the next character on this edge, which is a C, so I need to make a branch. I'll go ahead and make a new internal node. Our old branch was CABX, and this started at index 1. Our new one is just an X, which started at index 5 minus 1 is 4. We can verify that right here. That's BX. And so now, as I mentioned earlier in the previous example, but we didn't actually end up using it, since we did create multiple internal nodes in the same iteration, we have to actually connect them with a suffix link. So I'll do that in a new color. Like this. There's a suffix link between those two. So you'll see how this is useful later on in this example. And since we did add that that BX suffix, we can go ahead and decrement our remainder back down to 0. And our active length also will go down to 0. Since it's 0, we can effectively say that our active point is now again back at the root. So I'll go ahead and set this to null for clarity. All right, we're done with that iteration. So I can increment this to 6. Now we take in the A. So again, we will add that A to all the leaf edges. There we go. And we note again that this A already has an outgoing edge from the current active node, which is the root that starts with A. So we actually do not touch the tree, and we just set the active point to be right here, right after the A again. So since we didn't add a suffix in this iteration, I'll increment the remainder, and I'll also update this chart for where the active point is. So it's right after the A, which means from the root we take the edge, oops, wrong color, the edge starting with A and go down 1 unit. And we can now go to the next iteration, which takes us to iteration 7. We have a B. I'll add that B to all the leaf edges. And again, we notice that from our active point, the next character also matches that, the new one. So we just update the active point to right after the B. And in fact, since you'll notice that right after the B, we actually have an internal node. So what I'm going to do is going to change the entire active point to reflect that. So in cases like this, you can just safely set the active node to be, I guess I can color code this. So I'll say green is this node right here. So this is our new active node. Let's color that right here. And our new active edge will just be null because we're actually just at the node. So our new active edge will be null, and the new active length will be 0. So this green node right here is our new active point after that. And again, since we didn't add a suffix in this iteration, I will increment the remainder to become 2. Alright, so that's it for this iteration. I can go on to the next one, which is 8. Now we take in the C. So again, I will add the C to all the leaf edges. And from our active point, which is now this green node, we will notice that we do have an edge that starts with C. So we won't touch the tree again. We'll just update our active point to be right here, right after the C. So updating that in the chart, we now have, from the green node, we will take the edge starting with a C and go down 1 unit. Alright, and also, I forgot to mention, but we didn't add a suffix this iteration, so we'll increment the remainder to 3. Now we're done with this iteration, we can go to the next one, it's iteration 9. And we take in this D character. So I'll first add the D to all the leaf edges. And before I forget, I will also, technically this will increment to 4, but I'll just go ahead and add the edge for D right now so I don't forget. And that is starting at index 9, because there are no edges to start with D, so I can go ahead and label that here. And since I've added that suffix, I can decrement this back down to 3. So now we have a lot more work to do. We have to basically fix all these suffixes from before that we haven't touched. So that means we have to fix ABCD, BCD, and CD. So let's go ahead and do that. So from our active point, which is right here in red, right after this green node, we note that the D does not match the next character on this edge, which is an A, so we make a branch. So I make a new internal node. I had, before I had, let's see, I had A, B, X, A, B, C, D. me check that's right. ABC, ABX, ABCD. Yep. And its value was the same as before, 0. I have this new edge for just the D, which is represents the suffix ABCD. And that started at index 9 minus 3, which is 6. So now I've added this suffix successfully. I can safely decrement the remainder down to 2. And since the active node is not the root node, I actually won't be touching the active edge or the active length or anything like that right now. So at this point, since the active node is not the root, it's another internal node, what you want to do is you actually, if there are suffix links, you would take the suffix link. So that's what we're going to do right now. We're going to take this suffix link in blue and write it to the next node where we have to be. So when this happens, I will just take the suffix link to this new node. I guess I can color that in like red or something. So for this red node, now this red node is our new active node. So I'll go ahead and erase this. Our new active node is the red one. And our new edge and length will stay the same. So that's the beauty of this. We've kind of automatically found our new active point in order one time. We didn't have to start from the root node and search for it. We just kind of took the suffix link, kept the edge and length the same, and then that was our new active point. So there we are. At this point, you'll notice again that the D does not match the A that's on this edge after the active point. So we make a new branch. So I'll make an internal node. We have our old branch, of course, which was, I believe, A, B, X, A, B, C, D. Let me just make sure that's right. So you have B, C, A, B, X, A, B, C, D. Yep. And that had its old value of 1. We also have a new branch for just the new character D. And that would start from index 9 minus 2 is 7. And let me just make sure that's right. BCD. Yeah. Sweet. So we've added that suffix. And we can now decrement our remainder. But first, we should also do something which is add the suffix link, because we also created a new internal node before this one. And that was right here. So I'll go ahead and link them together. Might be a little messy, but bear with me. There's our new suffix link. And now we still have one more suffix to take care of. Unfortunately, we don't have a suffix link out of this red node, but we will soon. So what we have to do is, if we don't have a suffix link, we just jump back to the root, and again, keep the edge and the length the same. That's what's really amazing about this. It just all kind of seems to work. So now our active node is again going to just be the root. And from the root, we take the edge starting with C and go down 1 unit. And you'll note that that takes us to right where we have to be. So right now our active point is now right here. So let's go ahead and make the branch, since we know that the characters on the edge differ from the new character we're taking in. So I'll go ahead and erase all this. Make a new internal node. And we had 2 options. So one was our old branch, which was just A, B, X, A, B, C, D. That started at the old leaf value we had in this node, which was, I believe, 2. And we also have the new branch from the addition of the D. And that starts at index 9 minus 1, or 8. So, as per usual, since we create a new internal node in this iteration, we have to link it with a suffix link from the old one. So that was this node right here. We link those two together. And so if we ever need to in the future, we can just easily jump to it to fix another future suffix. So we've added that suffix successfully, so we can decrement our remainder back down to 0. I already handled the case where I added the edge for D, so that this all checks out. So now we're done with this iteration. We can just go on to the next one. Iteration 10. That gives us the $sign. And there's not really much to do here. We just kind of add that to all of the leaf edges. Hopefully I didn't miss any, but we implicitly added that to all the leaf edges. And now we note there's not really much to do here. We just see that there is no edge coming from the current active node, which is the root. This starts with a $sign. So we make one. And of course, this is the suffix starting at index 10. So there's our completed suffix tree for our example problem. It's a lot more complex and messy than the other ones, but you can verify that this is correct using some online tools for suffix trees or just drawing it out yourself. But yeah, you can see how clearly suffix links helped us avoid a lot of linear work when we had to find the next suffix to update. So next up, I'll be going over some of the rules for suffix trees that I kind of based this construction off of, and how they kind of help us reduce our runtime down to an overall linear runtime. All right, so this wall of text is just a quick description of all these steps and rules that Ukkonen's algorithm follows. I found that they weren't really that helpful for me, which is why I've opted to kind of teach in a example-oriented way. But if you're still stuck with something, feel free to consult the StackOverflow post, or Dan Gutsfield's book, or even Ukkonen's paper, all of which I'll be linking in the description below. So wrapping up here, I'd like to briefly reiterate why all of this was possible in order n time, and in specifically order 1 time per iteration, because that order n is inevitable. So the first trick we used was the edge representation change. So rather than storing each substring as a literal string, we just used a tuple of the start and end index from the original string. So for example, that would be something like this, where the start was index 0, end was 6. And what this allowed us to do was not only just save on space and time for creating all the strings, but we could also branch really quickly. So whenever we had to split an edge, say our active length was 2, and that means that our current edge's substring would just be represented as 0 to 2. Then we'd have another branch, maybe one. This would be the old original branch. That would just become 2 to 6, while the character that caused this branch would just be 6 to 6. So you can tell that all of this could just be done mathematically. We don't have to iterate over the string or anything like that. We don't have to create any new strings. It's just all simple math. Now, the next thing was the dynamic string endings. So that was, in my examples, I just used the $, but you could use anything. It could even be like a -1 or something. But what this allowed us to do was update all of the leaf edges in order 1 time. So typically, if we weren't using this, we'd have to visit all n leaf nodes and append that new character that we're processing to the end of their substrings. But since we're using this, that's all kind of taken care of implicitly for us. And then next up, we have the active point and the remainder. The active point, if you recall, was just telling us where in the tree we had to be. And since we were keeping track of that, we didn't have to search for where we had to be every iteration. We could just kind of know where we had to be in order 1 time and just go there. And the remainder kind of let us know how many suffixes we had left to process. So rather than rescanning the string each time we've added a suffix to find out what we're missing, we just kind of kept track of that. And that was pretty simple. And finally, suffix links were extremely important because they allowed us to take care of those cases where we had to take care of multiple suffixes at once in order 1 time. So instead of having to rescan from the root every time we made new internal nodes where the active node was not the root node. Instead of rescanning, we could just jump those suffix links. And since they're pointers, that's just order one time. We're not scanning the entire tree or anything. And we can resolve that suffix, jump to the next one, etc., etc. So that's how all of this was done in order one time per iteration. And since we had n of them, that gave Ukkonen's algorithm a total runtime of order n. Now, tying this all together, our original problem was to just find the longest common substring between multiple strings in linear time. And the way I chose to go about doing that was using a generalized suffix tree, which we saw earlier. Now, the problem was actually building that suffix tree in linear time as well so that we don't go over. And so we saw how to do just that using Ukkonen's algorithm. And the only thing we haven't talked about was actually just making a generalized version of a suffix tree, which is nothing more than, as we talked about, a suffix tree of more than one string. And so the way you could do that is just concatenate all of your original strings into one, make a suffix tree out of that, and then as you're building it, keep track of which of the original strings each of those substrings belong to. And I believe that could be done by using just the start and end indices of each of the strings, and maybe what iteration of the algorithm you're on, something along those lines. Anyway, you're going to have to take my word for it that this can be done in order m time, where m is going to be the length of the concatenated original strings, sorry. And yeah, that basically concludes this presentation. I hope you took something useful out of it. If not, feel free to leave some feedback in the comments section or in my peer review on web courses.